why do we have math in the first place? Was it invented by some nasty math teacher that just wanted to punish everybody with lots of homework and things that are difficult to figure out so we can continue to look for X? No, math was not invented in the classroom at all. As a matter of fact, as you're sitting there doing geometry or doing algebra or doing whatever kind of math, it's curious to think about, where did these things come from? And what forced us, or what motivated us to start figuring out triangles and figuring out numbers and things like that. So let's talk a little bit about what this stuff comes from, and we're going to start with probably what is the earliest math, which is geometry. So this is me more of thinking of history than it is of math itself. So geometry, the word comes from geo, which means earth, and then the word is metron, which means measure. So it's really just about measuring the earth. Well, that makes sense, but who was wanting to measure the earth and what was going on there? So if you think about the ancient Egyptians, 2000 BC, I mean, sometimes we're not real sure of these dates, but every time the Nile, we all know about the river Nile, right? So every time the Nile flooded, which was quite frequently, it wiped out all the property lines. So we own land around the Nile. We see this going on in rivers, anywhere, but the Nile, you didn't have GPS measurements or great surveying. As a matter of fact, you didn't have surveying at all to determine where the property lines were. So when my land gets wiped out by the flood, I want to know where my land was and where your land was. So they developed some methodologies that were simple to find their land boundaries again. And they started out with they knots tied equal distance in like a rope. And they use that to measure boundaries. And think about, if you've done geometry, the 3, 4, 5, the right triangle, the Pythagorean theorem kind of thing. It's the 3, 4, 5 triangle. So if you had a rope that's 3, tie a knot in it, and then 4, tie another knot in it, and then 5, tie another knot in it, and then you pulled that together, they knew that would form a right angle. How they found that out, I don't know, but they made this tool that was a triangle, essentially, to find the right angles and help them in land measurements. So these rope stretchers, as they were called, they were the people that went out there when it flooded and dried up a little bit, and they would go find the land, and they were called harpe danapate. Yeah, I'm pretty sure that's not right. But that translates really to surveyors. That's the first surveyors. So that's what they were doing, is they were acting as a survey to go find the boundaries of the line. So 1,000 years later, Greeks in the Alexander the Great and all the Greek society, they took up these practical tricks, and that's what they were. They were practical tools in a toolbox to help solve problems for the Egyptians, and I just gave you one of them. And they tried to think about why does a 3, 4, 5 triangle always work? They tried to answer the why questions about that, right? They did some exploring. And one man, particularly Euclid, around 300 BC, did some studying, and he wrote a 13-book masterpiece called The Elements. So when we study geometry today, and I'm not going to say modern geometry, but the geometry that we study, because there is a geometry past this, but you may have heard of us talking about or seen in your book Euclidean geometry. That's what we're talking about, is really based upon these works called Euclid's the Elements. So all of them are about that, and that's where we start getting postulates and proofs and things like that. And really it became, as he started pulling this together, it became not only the fundamental the design of geometry, it was the fundamentals of what we think of as modern logic. So now we know today there's some geometry that goes beyond what we think about as Euclidean geometry, but we don't really study that very often, or certainly not in high school very often. In this textbook, there is one chapter that gets into other types of geometries. That's the last, there's the last chapter of the textbook, or the last part of the textbook. So this Euclidean geometry, though, became the backbone of so much of mathematics that we were using it for architecture, astronomy, engineering. And today, it's fundamental in pretty much everything that we're doing. As you drive down the road and you're seeing how the roads are laid out and they're building something, they're building a bridge, it's all geometrically based, lined up. When they're building houses, geometry is all part of it. So if you've ever proved that two right triangles were congruent, or two triangles were congruent, you are using Euclid's elements from 2,000 years ago. So yes, much of what you're studying is a 2,000-year-old methodology or toolbox, if you will. All right, so that's geometry. That's where it came from. Very practical and still very hands-on practical. I think it's probably one of the most hands-on subjects that we got, because you can see and feel geometry so much and see it in so much architecture and buildings and even nature. So let's move from there to the study of algebra. Where do we get that? And that's usually what we're teaching first. And algebra, we're moving from, it's not just moving letters around. Algebra is about finding out what you don't know. And you always think about, we're trying to find x, solve for x. It's finding what you don't know. That's what it's about. The earliest forms of it that we go back are even earlier than Euclid, is the Babylonians. So when you think about the Babylonians, so much of this goes right back into Bible times, right? The Babylonian Empire, 1800 BC, so sometime around that time. We found clay tablets written in with the cuneiform, with word problems that said something like this: I have added 1/3 of my number and 4 to make 10. What is my number? So let me say that again. I have added 1/3 of my number and 4 to make 10. What is my number? That's a word problem that we would see in algebra today, and they were doing this for just apparently fun and enjoyment back at 1800 BC in Babylon. So if you translate that, that's an equation that I just gave to you. That's algebra. When we take, it's when you got a word problem, it always translates back to a equation, right? Because that's the algebraic notation. And so really what we were doing is taking these words. When I took algebra, when I was learning some of this stuff, I always hated word problems. I'm like, just give me the equation and I can maybe figure it out. But it really was word problems that we created a notation for that we call algebra. And that notation today is what we use for trade, construction, and everything else. It's just everywhere, right? And it's, as I've explained in other videos, you're using it all the time. You don't even think about you're doing it, because sometimes you're doing what this just said. I've added 1/3 of my number to 4 to make 10. We're doing stuff like that. Maybe not that. We wouldn't word it that way, but we are doing stuff like this at another time. But that's another video. So the word algebra itself, though, comes from Arabic. So it's Algebra, which sounds like algebra, right? But it's originally an Arabic word. It means the restoration or reunion of broken parts. So I'm trying to figure out the unknown equations, broken parts. It comes from a book written about 820 AD. So even though we were using these word problems, it's about 820 AD that we start formalizing it by a Persian mathematician named Muhammad. We won't worry about his last name. You can get the idea. He's Muhammad. He lived in Baghdad so this is after the time of Nebuchadnezzar. So we're at 820 AD. So it's after the time of the Christ and the resurrection. So this is considered the Islamic Golden Age. And so we're now in the Middle Eastern, so we're starting, I don't know what countries we were then, but at the time he was in Baghdad. Later becomes Iraq. So it was at a period of incredible learning, and a whole bunch of mathematics and science comes from that period, from that area, from Baghdad. So algebra was developed and formalized by Islamic scholars. That's where we get it from. So maybe you feel like sometimes it's written in Arabic, but they built this as a kind of a house of wisdom. They had like one of the great research areas of the world. This is way back then, right? There they translated Greek, Indian, Babylonian material into Arabic. So it was a university kind of model that was going on. And they taught how to solve equations, and what we now know as linear and quadratic equations is what they were teaching. Things like how long so these are some of the problems that you would see there. How long should each wall of a square courtyard be if we know the total area? Sounds like it comes straight out of Algebra 2 or Trig textbook. So the book that they built us gave us two words, algebra, and then the guy's name, it's Muhammad, but his last name is Al-Khwarizmi. That's not pronounced correctly either. But basically it translates into, or his name became the word algorithm. Okay, we get algebra and algorithm from the same guy, from the same research group. So every time you hear algorithm, and typically you hear this in computers or computer sciences, but you're saying his name. Essentially, that's a rough translation of his name. So that's how we get these two basic fundamental mathematics courses, geometry and algebra. Now, after this, we go back for 1,500 years. Euclid's geometry and our algebra that we have developed ruled the world. That was what we had. That worked really good. And think about it. What we're doing is we're solving common problems. Like I just said, we were doing geometric problems. We were doing algebra. Algebra was showing up in business. It was showing up with building, like the things solving for areas and perimeters and things like that. And you're starting to see a little bit of a combination of geometry and algebra together. But what was going on then? Now we're at the 1500s to 1600s. And so some things are different now is the Europe rediscovers all this ancient knowledge. There's a lot of turmoil during that time, right? But Europe discovers all this ancient knowledge. Explorers were busy sailing, discovering ocean, discovering new lands. This is the time when you start to see the Christopher Columbuses of the world, and this is we're just going, and Europe is going out, Spain is going out, doing all kind of things. So the explorers are sailing across the ocean, and they had a new set of problems. Is they need to calculate distance, direction, including curvature of the Earth. That throws another little. That's geometry, yes, but things get a little weird. Artists wanted to draw realistic perspective in paintings, so they would use geometry to show perspective, what we would consider dilation, and some of the things here in this textbook. I forget what chapter, but we go through that in the textbook. Then a man by Rene Descartes changed everything by combining these two. So all of these things were happening. He kind of formalizes the combination of algebra and geometry into what we would generally call today analytic geometry. we don't use that term a lot in terms of courses, but a lot of times that's what we're doing when we're combining algebra and geometry. For instance, if I was using equations to describe shapes, which we do a lot now, we would use something called the Cartesian coordinate system, right? So the Cartesian coordinate system, Cartesian from Rene Descartes. So the Cartesian coordinate system is named from the man that put all this together. So we draw X and Y graphs today, we plot things, and we're using algebraic symbols and geometry, pictures and shapes together, and it's built into one, here's a key word, language. Right? It's a language that we're using now to describe things that words can describe, but as backing with the thing, I've got two numbers I add together to get 10. It's clumsy, right? When I start describing things word-wise in a word problem, it's clumsy. Putting it into an equation is a much simpler way to look at it. Even if you're not that skilled in mathematics, I didn't understand much, but I knew that if I could get from the word problem to the equation, I might could solve it. It becomes easier. It's a translation of the problem into something that we can solve just by learning a little algebra and geometry. So in that sense, it's easier, right? Which is maybe a little hard to believe, but that's how so much of the things that we look at as complicated today it was an easier way of solving bigger problems. So now let's jump forward just a hair, a couple hundred years, into the 1600s. And scientists had another problem, is they had to describe where something was. Now we're sailing, we got the arcs of the earth, we got those kind of things. But now we need to describe where something was, but not only where it was, which is what they've been doing, but how it changed. Because what we were talking about before is location, position, shape, distance, time, things like that. But now we need to know how it changed. Like, how fast was the apple falling? How did the planet's speed changed as it orbited? How much water fill a tank as time passes? Geometry, and I'll give you something specific. If you take the apple in the tree that we think about with Sir Isaac Newton, and we go to the top of the tree and we drop that apple, the minute I let go of the apple, it's going 0, right? At the second. It is going at a speed of 0 miles per hour or feet per second, right? It's not moving at all, but it slowly begins to go faster and faster, and then by the time it hits you in the head, it's going at its maximum velocity. If you were way, way, way up high, it would be going about 120 miles an hour when it whacks you in the head. It's going to hurt. But between the time I let go of it and it hits you in the head, it has different speeds. It starts at 0 and it moves through or accelerates to 120 miles per hour, much like your car does, right? If I push the gas pedal, it goes from 0 up to whatever speed, but it doesn't do so instantaneously. It changes over time. So that became a question of where, as it changes over time, things don't happen instantaneously. What's their speed at different times? Or how do other things change? So really it became an issue of how do you measure change? These equations measure position and dollars and measure kind of static things, but now to find more dynamic or changing things. So two men, Sir Isaac Newton, that we think of, in England, and Gottfried, and I always say this, Leibniz in Germany, are the two inventors of calculus. Now, we usually give that to Newton, but it was two of these guys that were working pretty much independently that built calculus. they had some individual contributions, but they both were really accredited with calculus. So what they developed were formulas for what we would call instantaneous speed, which we now call in calculus derivatives, which is if after I drop that apple, 1 second later, how fast is it going? 1.2 second later, how fast is it going? 1.3 second later, how fast is it going? That seems kind of a ridiculously stupid question, right? Until we have to think about things like, as I blast a rocket into space, I do need to know pretty much all the time exactly how fast it's going. I need to be able to calculate that, because at the same time the rocket is going up into space and you're propelling jet fuel or propellants, you are the rocket is getting lighter, right? Because we burned up the fuel. So we got a change in how much the rocket weighs, a change in elevation, and a change in speed and acceleration. So there's a whole lot of changing going on. And because everything is very delicate, we got to get to the right speed at the right place and not overshoot, undershoot. We got to do these things correctly. This kind of stuff started to matter a whole lot. But even before then, I'm just saying, in modern science, this is really important stuff to us. So, but what we started with was just measuring gravity. Why does the whole law of gravity came from understanding? I mean, what you really need to understand it fully is calculus, because as we see, as we drop something, we see things go from zero to a different speed. They accelerate, and they accelerate. There's what's called gravitational acceleration. They accelerate due to gravity. So that's the things that Newton and them were struggling with. So they weren't really playing around with mathematics just because they were just geeky mathematics people. They were studying science, and they needed some tools that they could explain what was going on with a language that would make sense, and hence we have calculus. So now we go from there. We see modern industrial world that are around us, or digital world around us. Once you saw calculus get invented, you saw all kinds of things happen. Engineers used it for bridge design and machines. Physicists, chemists. This is the one that gets to a lot of people. Economists, financial people, business people, rates of change, the growth of markets, how much a market changes. Biology, what's the growth rate of a population, right? Or when we're talking about extinction of animals and things like that, that's population models. So there's rates of change. Computers are obviously so much built on this. So as we kind of close where we are mathematically, now we obviously have a lot more things and a lot more tools in the toolbox mathematically than we used to have, but these fundamentals that are still there, they were only created to help us solve problems. We, just like when we get English language, we needed to be able to communicate. When we're talking about mathematics in general, it is nothing but a language of communicating ideas about the world around us. And that's what we're doing. And we can just be thankful some smart people invented this so that we have these tools and we don't have to invent them ourselves. Because the one thing we do know about the more complex mathematics, it's very difficult to do this stuff by hand. So think about trying to run a space shuttle without calculus. Is kind of like adding and multiplying a whole bunch of big numbers without calculators, right? I can add and multiply a few numbers, but the calculator makes it so much easier, so much faster, and it's a great tool for this. And that's what we're doing right here in mathematics. So when you're driving down in your car today and you've got your phone on and it's telling you your GPS coordinates and what you're doing, that's calculus. That's calculus. As a matter of fact, that's why your phone gets hot. And that's why your battery wears out. It's so busy doing calculations that it just really sucks that energy out and gets hot. So you're using this stuff every single day. So you can thank these guys that have did all the work for you. Have a good one. We'll see you next time.